Section 2.5, this time we're starting to work with some more of those second derivatives, or those implicit derivatives, but this time we're going to work towards second derivatives. Question number 1 is kind of a review of things that we've already been working on, which is equation of a tangent line. So what do I need? I need a point and I need a slope. So if I was starting to write my solution, I've got this point. Let's put a 1 in when we see the y, and let's find the slope in a second, and let's put a 2 in for the x value. All I need is a slope, and I'll be in business. So how do I find the slope? I have to take the derivative. So let's do that derivative. I'm going to do it implicitly. I'm going to use product rule. So the derivative of x squared plus 4 times y is equal to 8 derivative. Let's take that x squared plus 4. Let's multiply it by the derivative of y. Derivative of y with respect to x would be dy over dx. Plus, now I got to take that y and multiply it by the derivative of x squared plus 4, which would be a 2x, equals the derivative of 8, which would be a 0. So now rearranging, let's take this and move it to the other side since we want to get dy dx by itself. Divide by an x squared plus 4. So I think my dy over my dx would be a negative 2xy divided by the quantity x squared plus 4. So now, why did we do this? We did this to find the slope. So my dy over dx, I'm now going to evaluate that derivative at the point that was given to me, which is 2, 1. So get used to this little notation right here. This means I'm taking the derivative at the point 2, 1. So everywhere I see an x, I'm plugging in a 2. Everywhere I see a y, I'm plugging in a 1. So in the numerator, I've got negative 2 times 1, which would be a negative 4. Denominator, I've got 2 squared, which is 4 plus 4, which would be an 8. So my slope of my tangent line would be negative 1/2. So I bring this over here, and there is my equation of my tangent line. Now, another thing that I could do with this particular problem, just to give people something else to think about, is I could actually define this equation explicitly instead of implicitly. Well, what does that mean? If I define this equation explicitly, that would mean I had y by itself. Well, this equation wouldn't be that hard to get y by itself. Y, if we divided by x squared plus 4, would be the same as 8 over x squared plus 4. Or y would be 8 times the quantity x squared plus 4 to the negative first. I'm trying to avoid quotient rule. So if I now took my derivative, we'll call it the red way, without having to do it implicitly, I'm now doing it explicitly. Negative 8 quantity x squared plus 4 to the negative second times the 2x, rewrite negative 16x over x squared plus 4 to the second power. So now when I evaluate this derivative, again at the point 2, 1, now it doesn't matter that y coordinate of 1 because I don't have any y's to plug it in for. So in my numerator, negative 16 times 2 is negative 32. Denominator, 2 squared is 4 plus 4 is 8 squared is 64. There's my slope of my negative 1/2, which matches my slope of negative 1/2 I found when I did it implicitly. So a little bit of, you got some choices there. One way is not better than the other. Do what you think is best. All right, let's take a look at this second derivative thing. Find the second derivative with respect to x. Second derivative. Before you can find the second derivative, you got to find the first derivative. So let's work on that. So first derivative, 2x minus 2y times dy over dx is equal to 0. Now it is imperative, if you were asked to find the second derivative and you're doing it implicitly, that you isolate dy dx before you try to do anything else. So let's subtract 2x to move it over. Let's divide by negative 2y. So my dy over my dx would end up being negative 2x divided by negative 2y, or in other words, my dy over my dx would be x over y. Okay, so there's my first derivative. Now what we're about to do is we're about to take the second derivative with respect to x. With respect to x. Well, that notation, if you take the derivative of something with respect to x, we're now taking the derivative of this with respect to x, and we're taking the derivative of this with respect to x. So if we go and do that, look at the notation on the left side of the equation. I've got what ultimately happens is we call this thing d squared y is what it looks like over dx squared. That is your notation for the second derivative. This thing right here is your notation for the second derivative implicitly. So now what does that really mean? Well, on the right side, take the derivative like you always have. So take the derivative. We're going to need quotient rule. So low would be y, d high would be 1, less high would be x, d low would be dy over dx, square the bottom and away we go. So there's your derivative, except now you never, ever, 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 ever leave a dy over a dx inside your second derivative. Instead, a little while ago, we found out that dy over dx was the same thing as x over y. Well, if that's the case, that x over y can get put into your second derivative and rewritten. So what I really have for my second derivative is y minus x times that dy over dx, which is x over y, divided by my y squared. And we got fractions inside fractions. So you know what I'm going to do? I don't like this fractions inside fraction thing, so I've got 3 terms. Let's multiply each term by a y so it cancels out my fractions inside my fractions. So if I do that, the first term was a y. We multiplied it by a green y, so here's a y squared, minus that second term on the top. The red y and the green y cancel out, leaving me an x squared. And on the bottom, the green y and the blue y squared become a y cubed. So this thing would be one version of your second derivative. Now, if you look that up in the back of the book, you look it up CalcChat, one of the things that they'll do is they'll go back, they'll take this and they'll go back and look at their original function. Let's go back and let's look at the original function. Well, the original function says x squared minus y squared is 16. Well, look at the numerator. We don't have x squared minus y squared, but we do have the opposite of that x squared minus that y squared. So what I really have in my numerator is I have the opposite of that 16 over the top of that y squared. We went back up here to the original function, and we found that x squared minus y squared is the same as 16. Well, we didn't have that. We had the opposite of it. So let's bring that back down here, and there's how I got my negative 16 over y cubed. Is one of those answers better than the other? No, not necessarily. There's not one that's better than the other one. It's just that when we have to go further, like a lot of times we do, horizontal tangents, vertical tangents, etc., which we'll get to in a few minutes, that bottom equation is going to be a lot nicer to work with than the top one is, just because of how many fewer variables we have. So one of those things, like a little note for you to make, is every once in a while look for a substitution of the original. Is it something we want to do every time? Well, maybe, if it makes it easier. If it doesn't make it easier, don't do it. So there's your there's some second derivatives implicitly.